Dr. V. Jayalakshmi is working as a professor in the Department of ECE, Anna University, Chennai. She has more than 17 years of experience in teaching. She has published more than 90 papers in international and national journals and conferences. She has organized more than 10 workshops and has attended more than 40 workshops and seminars. She has guided more than 100 projects in both UG and PG level. She is supervising 14 research scholars. She has established an AICTE sponsored MODROB project for VLSI Lab. She has an endowment award for the top rank holder in PG degree and has 4 cash awards for producing cent percentage of result in Anna University curriculum. She is a life member in various professional bodies like ISTE and IETE. She has specialized in mobile communication, microprocessor and microcontroller, digital system, computer networking, and neural networks.
Welcome to UGC lecture series, BSc Electronics Harness, Electronics Practicals 9, Instructions of 8085. In today's session, we will discuss about logical instruction, branching instructions and machine control instructions. In logical instructions, we are doing logical operations with basic gates, exclusive OR gates, rotate operations, complement. So, logical instructions which are performed with accumulator. One of the data should be loaded in accumulator, another data may be in register or memory, or it may be immediate data. These are the bitwise operations logically performed and the result is stored in the accumulator. In rotate, we can rotate the data either in right direction or in the left direction, with carry or without carry also possible. Then compare instruction in 8085 is available. One of the data should be loaded in accumulator, another data may be in register or memory. The two data is compared. Based on the flag register affected, we can read the status, either it is greater, lesser or equal. Let me discuss logical instructions. The logical instructions perform logical operations on data stored in registers, memory and status flags. The operations are AND, OR, exclusive OR, rotate, compare and complement. For AND, OR and exclusive, any 8-bit data or the content of the register or the memory location content logically OR with AND operation or OR operation or exclusive OR with the accumulator. The result is stored in accumulator. For rotate, each bit in the accumulator can be shifted either in left or right to the next position. For comparison, in 8085, any 8-bit data or the content of the register or the memory location can compare for equality, greater than, lesser than with the contents of accumulator. The results is reflected in flag register. Complement, it is nothing but NOT operation. The content of the accumulator can be complemented, that is just replacing each 0 by 1 and 1 by 0. This is a format for compare instruction CMP or M, which represents the register content is compared with the accumulator and the results are affected only the flag register. If both values are equal, then the 0 flag will affect. If 0 flag is set, we can say the accumulator content and the register content both are equal, otherwise not equal. In otherwise, suppose if you want to compare whether it is greater or lesser based on the carry flag. If carry flag is set means A is lesser than register value. If carry flag is reset means A is greater than the register value. The same thing can be performed accumulator with the memory by using CMP M instruction. So, based on the flag status, we can identify if A is less than the memory content or register content, the carry flag is set. If A is equal to register or memory content, the flag is 0 flag is set. If A is greater, then register or memory content, the carry and 0 flag both are reset. This is an example of instruction CMP B. So, B is compared with the previous data which is loaded in accumulator. CMP M means the HL register content which is in M is compared with the accumulator. The compare instruction can be performed with the immediate data also by using the instruction CPI 8-bit data. The given immediate data is compared with the accumulator content. Based on the flag register status, we can identify whether the accumulator value is greater or equal or lesser than the given number. Next format is AND gate. For AND gate, we are using ANA. ANA either register or M. In register, you can use any one of the general purpose registers which are B, C, D, E, H and L. Any register you can use it. That register content is logically AND with A accumulator, then the result is stored in the accumulator. Either the general purpose register or by using M you can access with the memory content. So, example ANA B. Suppose A value was 45, B value was 23. So, how these two are logically performed? So, first we have to convert into binary value 0 1 0 0, then 0 1 0 1. For B we have to write 0 0 1 0 0 0 1 1. What is the function of AND gate? If any one of the input is low, the output is low. When all inputs are high, the output is high. So, here both inputs are 1, output is 1. Here 0 and 1, the output is 0. 1 0 0, both are 0 0 0, here 0 0 0. So, finally, the resultant value was 0 1. So, after executing that, the accumulator value was 0 1. So, this is the logical operations which are performed in the bitwise. The corresponding content binary representation will logically AND with the register content. Logically AND means it will satisfy based on the truth table. This is another format for AND operation. The accumulator content can be directly performed with the 8-bit data by using this instruction ANI 8-bit data. So, the given 8-bit data directly logically AND with the accumulator content. Result is stored in accumulator. This is the example ANI 86. So, the unknown value which is in accumulator logically AND with the given immediate data 86. After that, the result will stored in the accumulator. Another one is interesting operation which is exclusive OR. In the exclusive OR, what is the truth table for exclusive OR? When both inputs are same, the output is 0. When different inputs are applied, then the output is 1. That is both A and B, 0 0 or 1 1 means it generate the output as 0, either 0 1 or 1 0, the output is 1. So, based on that we are operating the exclusive OR. Here one of the data should be loaded in accumulator, another data may be in any one of the general purpose register or with the memory content, or you can perform with the immediate data with a different mnemonic format. So, this is the example XRA B. We will consider the example. Suppose I am giving XRA B, right. A value was 23 which is already loaded, now B value which is 47, right. So, we have to do the binary representation 0 0 1 0 for 2, 0 0 1 1 for 3. Similarly, for 47 0 1 0 0, then 0 1 1 1. In exclusive OR, when both inputs are same, the output is 0. So, here both inputs are same as 1, so output is 0. The next two bits are also same, so the output is 0. Here 0 1 different input, so we get the output as 1. Here both inputs are same, so 0, same input 0, different input 1, different input 1, same input 0. So, finally read it as a hexadecimal which is 6 4. So, after that the 64 is stored in the accumulator. So, after executing this instruction, the accumulator content will be varied. Before the execution we are loading our required data, after executing the resultant value will be stored in the accumulator. Next instruction is ORA, that is for OR gate. For OR gate we have to know the truth table, what is OR function. In OR function, when any one of the input is high, the output is high, otherwise the output is 0. So, based on that, one of the data is loaded in accumulator, another data may be in any one of the general purpose register or the memory content. The given register content logically OR with accumulator and the result is stored in the accumulator. Now, we will see the example ORAB or ORAC or any register in any one of the general purpose register you can use it. Now, how the logical OR functions will perform. So, the previous value A is equal to 33, then consider B is equal to 71. Now, 0 0 1 1 0 0 1 1, for 7 0 1 1 1, for 1 0 0 1. Now, we have to do the logical OR operation. In logical OR operation, if any one of the input is high or 1, we get the output is 1. So, 1 1, so output is 1, 1 0, output is 1. Here both inputs are 0, so output is 0, then here 1 1 1 0. Finally, read it as 4 bits, so 7 3. So, the answer is 73, which is loaded in the accumulator. This is another format for logical OR operation, ORI 8-bit data, that is the given immediate data is logically OR with the accumulator and the result is stored in the accumulator. This is the example ORI 86. So, the given 86 value, whatever the unknown content in accumulator may be logically OR and the result will stored in accumulator. Another logical instruction is RLC. RLC means rotate accumulator left. Each binary bit of the accumulator is rotated left by one direction. So, bit D7 is placed in the position of D0 as well as in the carry flag. The carry is modified according to the bit position of D7. So, the format is RLC, it represents the accumulator content is rotating in left direction. So, while executing there is no affection of the sign flag, parity flag and 0 flag. The next instruction is RRC, rotate right accumulator. The accumulator content is rotating in the right direction. So, while right direction D7 become D6, D6 become okay. The accumulator content which is a 8-bit content. So, rotate right direction means the D7 bit position will shifted to D6, D6 position will be shifted to D5. Similarly, the D2 is shifted to D1, D1 will be shifted to D0. So, the D0 which is LSB will be back to the D7, LSB will back to the D7, this is a rotate right direction. The next instruction is RAL. RAL is rotate accumulator through the carry. Accumulator through the carry means the same register values rotate left means D0 is passed to D1, D1 to D2, similarly D6 to D7. The MSB data which is a bit position D7 will be back to the D0 via the carry flag. If suppose any content in the carry, the D7 is placed in the carry flag content will be comes to D0. So, RLC is rotating accumulator, RAL is rotating accumulator with carry. The next one is CMA. CMA is complement, it is like a NOT gate. So, the content of the accumulator are complemented, no flags are affected. Complemented means just inverting 1 by 0 and 0 by 1. The format is CMA. The next instruction is CMC, which is used to clear the carry flag. Either set value can be reset by using the CMC instruction. The carry flag is complemented, no flags are affected by this. For set carry we can use STC instruction. The next one is branching instructions. Branching instruction means it will switch over from the current location to another location. So, how it will switch over? Either within the main program or to the sub programs. While before switch over to the specified location, whether it will check the flag register status, then it will take the decision, means then it called by conditional instructions. Otherwise, it is a unconditional instruction. So, during the branch instructions, the flow of program counter will be varied. While starting executing, the starting address of the program will be stored in the program counter. When we are using the branching instructions or after reading that instruction, the current value of the program counter will be loaded into the stack pointer. Then the current address where to switch over will be loaded in the program counter. Now, the program counter will start with the new instructions. After reading return instructions or after meeting the condition, it will pop the previous address from the stack pointer, then it will return back to the main program. That is the main function in the branching instruction. The branching instruction is controlled by the program counter and stack pointer, or the sequence of the program is executed by using stack pointer and program counter. The next instruction in a branching is jump, JMP 16-bit address. This is one of the unconditional instruction. The program sequence is transferred to the memory location specified by the 16 address given in the operand. The memory location is nothing but program counter. So, JMP 2034. So, after executing this without checking any flags, the 2034 will loaded into the program counter. Then the program execution start from 2034, 35, 35, 35 and 36, continuously it will execute. There are three unconditional instructions. One is jump instruction, another one is call instruction. Call 16-bit address. This one is used to call the subprograms. The program sequence is transferred to the memory location specified by the 16-bit address given in the operand. Before the transfer, the address of the next instruction, after the call, the content of the program counter is pushed into the stack. Example, call 2034. So, after executing that, the current value of the program counter is loaded into the stack pointer. The new value, which is 2034, will loaded into the program counter. Now, the program counter will execute, and the main program call will be terminated by return instruction. So, after reading the return instruction, it will pop the data from the stack and return to the main program. So, this is the third unconditional instruction, which is RET. The RET is return unconditionally. It is mostly used in the last line of the subprogram, which is used to terminate the subprogram. The program sequence is transferred from the subroutine to the call program. The 2 bytes from the top of the stack are copied into the program counter, and the program execution begins with the new address. So, in unconditional instruction we have 3: jump, call and return. Conditional branching instruction, it will take the decision based on the flag register. So, this is JZ depends on the 0 flag. JZ represents jump 0, 16-bit address is a conditional jump. If 0 flag is set, then it will switch over to the specified location. So, JZ 2034 means if 0 flag is set, then it will switch over to 2034, otherwise it will continue the remaining lines. So, these are the unconditional instructions which are JC. Depends on the carry flag. If it is set, then you can take jump on carry. If it is reset, then you can take it as jump on no carry. Based on the sign flag, if sign flag is 0 means jump on positive, if sign flag is 1, jump on negative or minus. It depends on the 0 flag, we have the 2 conditions: jump on 0, jump on no 0. If 0 is 1, it represents 0 flag is set, so jump if 0 condition is met. Based on that parity flag, it will take the decision either odd parity or even parity. P equal to 1, it represents even parity. So, jump if even parity condition is occur. JPO is jump if parity odd when the parity flag is reset, 0 represents reset. The last one is control instruction, which is used to control the processor. So, one of the special instruction in this is NOP. NOP is no operation, it does not perform operation, but we are using within the program to make the delay. So, no operation is performed, this instruction is fetched and decoded, but no operation is executed. Whenever we want delay, we can use this instruction NOP. Another important instruction is halt, which is used to terminate the main program. After executing that, during the execution, after reading the halt instruction, it automatically terminate the sequence of the program counter. This is a format HLT, which is halt. The CPU finishes executing the current instruction and halts any further execution. On interrupt or reset is necessary to exit from the halt state. In today's session, we have discussed the logical instruction, branching instruction and machine control instructions. In logical instructions, we have discussed about the basic gates, which are AND, OR, NOT, along with that exclusive OR gate. Then the shift operations, which is done by the rotating either in the right direction or in the left directions. The branching instructions, which will change the flow of execution, depends on the flag register or independent of the flag register. Based on that, we have discussed conditional branching instruction or unconditional branching instructions. Finally, some instructions which are used to control the processor, which is name it as machine control instructions. Questions: what is resultant value of XRA A? Second question, MVI A, 36 RRC, what is the accumulated value after executing this instruction? What is CMC? Write the difference between RET and HLT instruction. Thank you.